In this video, I'm going to remind you of some of the basics of rational and real numbers. You might remember that the set of rational numbers is denoted by Q and consists of ratios of integers. So P and Q are integers, are numbers from the set of integers. And of course, we don't want to divide by 0, so Q shouldn't be equal to 1. So we have these fractions making up the set of rational numbers. Of course, you have seen many examples in your studies, but let me just give you one rational number, that is the number 2, because it can be expressed as a ratio of two integers as 2/1, but it can be also expressed as 8/4. So you can already see that there are many ways of expressing the same rational number. And this is why we usually assume that P and Q should have no common factors. So usually assume that the fraction is already reduced, so P and Q have no common factors. Numbers that divide both P and Q other than the number 1. So I should make a remark at this point. How do we see rational numbers introduced? Well, they usually pop up as solutions to linear equations. So if I consider this linear equation for x being the unknown, 3x plus 1 equals 0, you can quickly solve this equation for x and you get the result, the solution, which is negative 1/3 minus 1/3. So that is a rational number. So rational numbers arise as solutions to linear equations. Linear because we have the first power of the unknown in the equation and no higher powers of x. So, but we can easily find equations which have no rational solutions. So this is a proposition that I'm going to prove. Namely, I will prove that the equation x squared equals 2 has no rational solutions, meaning that there is no rational number which squares to 2. So the way we are going to prove this proposition, you might have seen this proof before, is an indirect proof or proof by contradiction. This is a different way of proving statements, different to proof by induction. So it's a proof by contradiction. The main idea behind this proof method is that we are going to assume the opposite of our statement and then make logical steps and arrive at a contradiction, meaning that somewhere we made a mistake, we assumed something that is actually not true, and since each step is going to be correct, it's only the very first assumption that must be false, assuming that, for example, in this case, there is a rational solution. So let's do that. Let's assume that there is an x in the form of P over Q, a rational solution, such that it squares to 2 and P and Q are integers with no common divisors. Just like we have introduced rational numbers. So we are assuming that there is this rational number x, which squares to 2. let's see where it takes us. So if x squared is equal to 2, that means that p over q squared must be equal to 2. Multiplying by both sides by q squared gives us p squared equals twice q squared, which immediately tells us that p squared is even. Is an even number because it's twice some integer. But if p is an even number, that can only happen if p squared is an even number. That can only happen if p itself was an even number, because an odd number multiplied by itself results in an odd number, so p must be even. But if p is even, that means, well, that's the same thing as saying it's twice some integer, so I'm assuming that m here is some integer. Okay, and let me go back to this line. Now if I substitute 2m for p, then I have 2m squared equals twice q squared. Now I have basically 4m squared by raising, squaring each factor in this 2m equals 2q squared. Now I can simplify by 2, so I have 2m squared equals q squared, meaning that we are at a similar position than we were at this point. Now we see that q squared is twice some number, so is an even number. And just by the same argument, we have that q is even. But so it could, for example, be twice some number n, some integer n. But that, of course, means that p and q have a common divisor, and that is the number 2. So this contradicts our assumption. We have arrived at an assumption by finding that p and q have a common divisor. They are both even. So our original assumption of saying that there is a rational solution must be false. So there is no rational solution to this equation, meaning that this number, which would square to 2, must be not rational. This is an irrational number. So my task to you, so I would like to test your understanding. So again, pause the video, and below the video you should see this these options appearing. So please choose which of the following numbers are rational. Okay, so I will give you 3 choices. So option A, well, the number A is root 2, is the number that squares to 2. B is root 3, and C is square root of 4. Okay, so I want you to remember what we have done, and maybe try to see what about these other numbers, and after you have selected the rational numbers, I will give you the answer. Okay, so the first number, root 2, is just this number that we have talked about. So this equation, x squared equals 2, has 2 solutions, plus or minus root 2, but they are both irrational, they are not rational. And similarly, if you have looked it up or have gone through the same proof, you could see that the square root of 3 is also not a rational number. And finally, well, you might know this one already, that of course there is such a number. Actually, there are 2 numbers which square to 4 plus or minus 2. So this last option is a rational number. Okay, so I'll see you in the next one.